Good morning, everyone. Thanks for coming to the presentation. EviHunter identifying digital evidence in the permanent storage of Android devices via static analysis. My name is Chris Cheng, from a PhD student from Iowa State University. This is a joint work with Chen Shi and my advisors, Professors Niu Zhenxianggong and Professor Yong Guan. This project is cooperated with NIST researchers Barbara Goodman and James Lyle. The project is sponsored by CSAFE, the NIST Center of Excellence in Forensic Science, which is also the largest forensic science center in the United States. Okay, let's get started. In the last year, a statewide largest animal poaching case was discovered in Washington State, the United States. Dozens of animal illegal kill sites were found. Animal poaching, which is the illegal hunt of wild animals, is a serious crime. In this case, there are over 190 charges toward the men involved in this case. And each of them received at least one felony charge and one misdemeanor count. So, what kinds of evidence are found to support the charges? Well, let's look at the forensic investigation of this case. First, the forensic practitioner obtains the suspect mobile device, and then the file system image was extracted from the device. Then, the evidence identification is performed on the extracted file system image. In this case, there are two crucial pieces of evidence were found. The first one is the GPS coordinate extracted from photos. Here it is. According to the GPS coordinates, the law enforcement identified the shotgun slug, which is the bullet, and it will be the most important evidence if it is matched to one of the suspect's gun. The other piece of evidence is a text message. According to the text message, the suspect told his mom about a 4-hour chasing against a bear and finally got it killed. Let's look at another case of the UIUC kidnapping case in last year. A 26-year-old Chinese visiting scholar was reported missing in the University of Illinois at Urbana-Champaign. Later, the police department changed the case into the kidnapping case and believe the victim is no longer alive. So, what makes the police have such speculation? Well, it's the evidence. So let's look at how the forensic investigation was performed in this case. First, Sam obtains the suspect mobile device and extracts the file system image, perform the evidence identification in the extracted image, and in this case, the crucial piece of evidence is web browsing history. According to web browsing history, the suspect used his phone to visit the website Abduction 101 and asking a question regarding the perfect abduction fantasy, which support the motivation of kidnapping. So both of these two cases help us define the evidence identification problem, which is the research problem of EviHunter. That is, given an image of a device file system and a type of evidentiary data, identify the files contains the type of evidentiary data. Well, people might argue there are several existing approaches can solve this. For example, the first one, the naive approach, is the manual analysis. The forensic practitioner can look into the file system and review the file one by one to see if there is desired interested type of evidence. Well, the drawback is apparent. It is time costing. So they might choose the smarter solution, which is the second one. They might use the mobile forensic analysis tool such as a Cerebrite UFED to perform the string pattern analysis or keyword searching. Well, it is error prone when meeting a large number of files give you a quick idea of how many files in an Android device. A regular use 5-year-old device had been extracted around 20,000 files. So both of existing approach now work pretty well in the evidence identification problem. Also not in the permanent storage, but another approach is worth to mention is the GUI-tar published in the CCS 2015. They propose to leverage the memory forensics to recover or reconstruct the graphical user interface of mobile apps from the dump memory data. So since the existing approach does not work pretty well in the evidence identification problem, we propose our own approach. Our approach can be separated into two major parts. First, it's an offline part. We propose to use App Evidence Database, as known as AED. So each row of the database contains the app's identifier, which is the package name, the file path, which is the evidence location, and the corresponding evidence type. For online part, taking the file system image as input, we query the AED with the, for example, the interested type of evidence, for example, the browsing history, and then so that we can get back the query result of the file path and we match against the file system image of the suspect device, so that we can output the file if it is founded on the suspect device file system image. So basically, the online approach is just a simple file path matching problem. The challenge part in our approach is the offline part, which is how to build AED. To build AED, we propose to use static program analysis and to analyze each app to answer two questions. First, what kind of evidence are there? Second, where they are, which is the file location. Well, by using the static program analysis technique to answer these two questions, there might have several technical challenges. First, the file path which is constructed by string cannot be fit in the IFDS problem, which is a general framework in the static program analysis, so that we cannot use the existing IFDS solver to solve our problem. The IFDS is defined as interprocedural, finite, distributive subset. Since the string is neither finite nor subset, we cannot use this. Second, the file path is implicit, unlike the constant in the program. The constant which are long or integer or double, but the file path is implicit because there's no class in Android dedicated for file path. The file path existed in such as print writer, file output string, file writer, and so on and so forth. So basically, the file path construction is heavily depend on the system API. How do you handle the system method? Because most of the operations are finished inside the system API. Third, the file path can be dynamic. I will put a slide addressing these issues later, but at this time, I will give you a quick idea. For constructing a file path, what about there is a case that this string is come from the return value of the current time minutes? Fourth, the file path requires to be the path sensitive, which means we treat the if-else two different branch as two individual cases. In that case, since the file path is sequence sensitive, right? For example, if the if branch has append the file path with .txt, the else branch append with the .jpg, you cannot merge this together because it will cause the error of the file path. So let's look at the existing tools. We argue that existing tool cannot build AED. Most of existing tools are focused on the privacy leakage problem, which are summarized in the right-hand side. For privacy leakage problem, we're given the sensitive information source, such as GPS and time, and we're given the sink, such as the file system sync method. We will see by applying the propagation rule if the sensitive source will meeting the sink. At last, if yes, then we will report it is privacy leakage. But in this problem, we select two representative work, which is FlowJoy, which implements IFDS solver as its core algorithm, and JoySafe, which implements their 10 propagation logic inside the thousands of the system library. So in this case, both of these two tools cannot solve our problem. Therefore, we propose our own program analysis approach, which is EviHunter. Let me give you a high-level picture of EviHunter. First, we take the input of Android APK file, and then we extract the code from the APK file. Then we perform the forward analysis toward each statement at each program path. And then by applying our propagation rule, which is separated into two major parts, the method invoking statement and non-method invoking statement part. And then finally, when reaching the sync method, we report both the file path and evidence type information. So during the analysis, we keep tracking the text structure of each variable, which contains both a path, which is a string variable, and EV_set, which is a set of booleans using to detect if evidentiary data is potentially carried with the variable. And using the right-hand side example, at line 1, suppose there are location information propagated into this method by the GPS long and GPS let. At line 3, a file output string object sync is created by using the file name in line 2. And in line 9, finally, the variable str, which is potentially carried with the location and timestamp information, was written into the file system. I will use this example to explain our propagation rule in the following slides. So as you can see in the line 9, we report the file location from the invoke instance object's text structure and the evidence type from the argument. So let's first look at the non-method invoking statement. For non-method invoking statement, we give you an example here. VA equals VB to VC, while VB and VC are string. In this case, we simply just make a string concatenation of the text path part. But for the EV_set part, since they both concatenation together, so if there are evidence information inside the VV or VC, then we make a union of two text EV_set variable, and we send it back to the VA. So let's use the line 7 and line 8 in the previous example to explain this. As you can see, the tag str, the EV_set, will be the result of union of location information and time information. So let's explain why at line 9, which is a sync method that we send out the variable to the file system, will be reported as carry the location and information evidence there. So we also implement a lot of propagation rule about the non-method statement, but to save the time, I will not talk about the complete list here. So for the method invoking statement, by default, we implement the inter-procedure analysis. But as you know, there are thousands of system API there. So it is inefficient to analyze a certain system API again and again. Therefore, we summarize the data flow effect of each API. In today's talk, I will focus on the file construction part. The system API for constructing the file path in Android is majorly separated into two parts, which is a soft-coded approach and hard-coded approach. For the hard-coded approach, you can see and observe the complete path information in the system API, right? As you can see in the first argument and the second argument, the result will be their concatenation result. But for the soft-coded, you cannot see the complete information there. In this example, you can only see the file name there. So that we will have to concat /data/package name /files, and we put it at first, and then put the file name at last. So that we will need to handle this kind of soft-coded approach in the system API. Since this is the same as the motivating example, let's explain why we can get a complete file path at line 5. And there are also dozens of this kind of system API in Android. So we manually review all kinds of this API in the Android developed document, and we summarize the data flow effect for them. So here comes another question. If there is a dynamic string reset in the file path, how can we handle that? In this example, the hard-coding approach take the timestamp as an input. And in this case, since we didn't handle the dynamic string, we will get an empty string in the file path, which will result in error. Therefore, we manually summarize the 100 preliminary result that contains the empty string, as you can see in the first line. So we get a result that the top 3 category of dynamic string is intent, timestamp, and UUID, which is a random number. And then we assign them with a special label so that after replacement, you can see it changes into a timestamp.txt. So we put the EviHunter to test on the benchmark app at first, and later we deploy it to analyze the real-world apps. We in total collected more than 8,000 real-world apps. And from our real-world app analysis result, we find that the popularity of app does not relate with whether this app will generate evidentiary data. And second, the shared preference, which is simple map structure files in the Android system, is the most frequently used to store the evidence. Third, time is the most frequent used evidence type in the file system. And we also do the manual verification of 557 files, and we get a result that 90% of precision and 89% of recall. So if I stop here, then people might challenge me that what's your difference with the 10 analysis result? So we provide you the most amazing analysis result in our approach. First, let's take a look of these 2 pictures. What do you think of these apps are? Actually, it is an app for celebrating the Indian festival. It's a traditional festival for the Happy Diwali. And you can use this app to play the music or use the wallpapers. The second, this app, it is just a simple gaming app. And you can toast the sandwich or baking the burgers there. So what's the special of I displaying these 2 apps for you? Actually, these 2 apps will track both the location and time and store this in the file path. Suppose today we don't have the file path result. Then after you get 133 apps like this, you will just make a conclusion that, oh, there are just 133 apps will store the location and time information in the file system. But with this, one will curious that why 133 apps will write the same data to the same path? Well, we do the manual verification to prove our analysis is correct. So we take out our device, we initialize it, to make sure there's no file path contain this kind of data, we install the gaming app to this device, and I play this game for 3 hours. And here's we extracted a file path. We prove that there indeed has this file path, and it keep already tracking your GPS coordinates. So what does this mean? We trace back from the class, and to see what results in this kind of interesting result. And using the class name, we trace back to a website that is from the Airpush advertisement developer document. And this document brings us back to the docs.airpush.com, which means this is the advertisement library for Airpush. And then the amazing part is here. The Airpush library say they have 450 million users. What does this number mean? We have 4.5 billion mobile users in the world, which means 1/10. Suppose today we have 200 people here, then I can say 20 of you, your device carry the location and the time information in that ldata.db. So here comes the interesting part. If you are a student like me, then you should be very careful of this finding. Because of what? If I was your advisors, after I watching the YouTube video, I will ask you to prove that, okay, show me that you pay very attention in the CCS conference in these 3 days instead of sneaking out and playing around in Toronto. So let me make a quick summary of our approach. First, we formulate a new mobile forensic problem, which is the evidence identification problem. Second, we develop a static analysis tool to solve this, which is EviHunter. Third, there are also other further research questions that can be worked on this, such as you can classify more dynamic file paths and improve the efficiency of this. Thank you.
So do all apps save the evidence in a permanent storage? Are there apps that don't do that?
Are you asking if all the apps are storing the evidentiary data in the permanent storage?
Yeah.
Based on our evaluation result, we found that just half of them will save the evidentiary data in the permanent storage, but it doesn't mean the rest will not. Somehow, for example, the logging system, which is a memory, it is a memory forensic part, but it is not a permanent storage. But you can also find some evidentiary data there. Yeah.
Do you look at? Oh, okay.
I have one question. Sometimes some sensitive evidence file can be encrypted via key used by application.
Yeah.
In this case, how can you analyze?
So we are discussing if the this encryption function exists in the program code, if the EviHunter is still working on that. Well, so it based on how we summarize the data flow effect of the system API, if it use the system API to encrypt it, right? But if it is not, then you implement the encryption function by yourself. Then it depends on how data flow analysis will be performed for that function. If it is kind of an implicit flow, which is a very special term in program analysis, then I will say it is very hard to detect.
Probably this is possible, but some critical applications such as instant messenger application usually hide their encryption logic with some parameter generating encryption key. So in this case, it is quite difficult to collect just a file from external paths.
Well, so regarding the encryption part, since our tool is mostly focused on collecting all of the real-world apps evidentiary data, for encryption, there might be, especially in malware, but that is not the mostly focused part in EviHunter. But we will see if there is some improvement that we can make for the encryption function.
Okay, thank you.
Yep.
Did you consider the privacy implications of your tool?
I'm sorry?
Did you consider the privacy implications of your tool?
Privacy implementation?
Like privacy implications, that it's saving all this data and you're providing people a way to access kind of sensitive data, right?
Yep.
So
if
someone want to be private and they don't want this data to be
actually
accessible.
You can also leverage EviHunter as a privacy leakage tool that you can defend the attack, such as the way you are talking about. Yeah, I think it is a very good point to extend EviHunter.
Okay, let's thank our speaker again.
Thank you.